Those aren't working right now, so you're probably going to just listen to my class. Okay. I mean, I'll be muted, so.
All right. Almost everybody's back. Just waiting for GK. Good review. I won't make you report on what you talked, but good review. Everybody's good? Got a basic idea? Okay. All right, so today what we want to do is look at what happens if our eigenvalues are complex. So it's going to be the same basic process at the beginning, the determinant, the finding the eigenvalues, etc. But then if we get complex numbers, we want to know what happens. So that's today, complex eigenvalues. Complex eigenvalues. So we could do this the same way that we did it before, right? We could still go through, find particular solutions, and then smush them together to make a general solution. But the problem is that if our eigenvalues are complex, then we are going to have complex numbers in our answer. And again, our original problem didn't have complex numbers in it. So we don't want to introduce complex numbers into our new problem. So we're going to do what we did last time when we did this with a regular equation. We need to recall how to deal with e to a complex number. So remember that e to the I times mt, you can split that up, cosine of mt plus I sine of mt. I think that's called Euler's formula. I think that was we called it the first time around. So Euler's formula, all right? And if lambda is a complex eigenvalue, this will make more sense when I do an example, but I just want to say it first. If lambda is a complex eigenvalue, then we're going to say x1 is the real part of x, and x2 is the imaginary part of x. And remember what x was? X is e to the lambda t times v, right? That was my x, e to the lambda t times v. Hopefully you said some of those letters in your breakout rooms when we were going through. So you find lambda, you find v, you make it into an x, and what we're going to do this time is split this into real and imaginary parts. So this is kind of cool, actually. Notice what's going on. We're getting two different solutions for a single eigenvalue, which means we kind of sort of only have to do half the work. And the reason for that is because also remember that if lambda is a complex eigenvalue, I'm not sure if I introduced this notation. Lambda bar is also an eigenvalue. Remember, eigenvalues come in pairs. So lambda bar is the complex conjugate of lambda. I think I used that terminology way back in chapter 2. You don't have to nod at me. I wouldn't expect you to remember. But basically, remember that we are saying lambda is a plus or minus b times I. So we only have to deal with one of those. We only have to deal with the plus, or we only have to deal with the minus, because we'll get the same answer for the other one. I'm talking in generalities. You are thoroughly confused. That is totally okay. This will be better when we do an example. So I've got two examples that I want to run through today in order to show you how this works. Let me not ask on questions right now, because anything that you have is not helpful. You're very nice people, but I haven't done enough of an example yet to tell you have good questions. So let's do an example. Here we go. x1 prime is 3x1 minus 4x2, and x2 prime is 4x1 plus 3x2. x1 prime is 3x1 minus 4x2. x2 prime is 4x1 plus 3x2. And what we want to do is find a general solution. x1 prime is 3x1 minus 4x2. x2 prime is 4x1 plus 3x2. Find a general solution. First of all, we have to check that we can use the eigenvalue method. So 2 things that you have to check. Homogeneous. Yes, is this a homogeneous system of equations? Homogeneous? Yes, nod at me. Yes, give me a thumbs up. Tell me this is homogeneous. Yes, yes. Okay. Second, we need to have constant coefficients. So we'll check off homogeneous. Nod at me. Yes, give me a thumbs up. Yes, constant coefficients. We have constant coefficients. Yes. Okay. All right. So we want to use the eigenvalue method. Since we can do both of those, we want to go with the eigenvalue method. And that means I need 0 to be equal to the determinant of lambda I minus a. That's my equation that I need to figure out the eigenvalues. I'm going to jump. You guys can jump here if you want to also. So this is the determinant of lambda minus 3, positive 4, right? Because it would be 0 minus negative 4. So this turns into a positive 4. Negative 4 and lambda minus 3. If you're not sure where those are coming from, write out the previous step. Lambda 0, 0, lambda minus your matrix that you have. Okay, so this is lambda minus 3 squared minus negative 16. Lambda minus 3 squared minus negative 16. And I am going to assume that you can FOIL and combine things. Lambda squared minus 6 lambda plus 25. Lambda squared minus 6 lambda plus 25. Does not factor. That's sad and unfortunate. I'm also going to trust that you can do the quadratic formula. So this gives me lambda equals 2 plus or minus. That's wrong. That's the other example. Let's go with lambda equals 3 plus or minus 4i. Sorry, I was looking at 2 examples. We're doing another one. Lambda equals 3 plus or minus 4i. I'm trusting that you can do the quadratic formula and get to those values of lambda. 3 plus or minus 4i. All good so far? Everybody okay? All right, here is, it's still the same, but it's a little more convoluted because we have complex numbers. So remember, I could use either one of these. It doesn't matter. I'm going to go with the plus. So let's plug in and we will have an augmented matrix, right? And remember, I'm not going to bother to write down the zeros on the right-hand side because they just stay. No big deal there. So this is going to be 3 plus 4i minus 3, 4, negative 4, 3 plus 4i minus 3. Plugging in lambda to your matrix. 3 plus 4i minus 3, 4, negative 4, 3 plus 4i minus 3. Okay, we can simplify. So this gets me 2, 4i, 4, negative 4, and 4i, if I simplify. Okay, tip at this point in time. It is way easier if you have a real number as opposed to a complex number in the top left. That top left number is called your pivot. It's what you use to zero out the entry below it. And it's way easier if that pivot number is real as opposed to imaginary or complex. You can do it if you have an imaginary or complex number in the top. It's doable. It just requires more thinking and more algebra. So since an elementary row operation that's legal is to switch 2 rows, I'm going to do that. So we'll switch row 1 and row 2, and that's just going to make my arithmetic a little bit easier. So that's going to give me negative 4, 4i, 4i, positive 4. Just easier to have a real number up there. I think there's some examples in the book where they do it with a complex number up there. It'll work. It's fine. I'm just trying to make your life a little bit easier because I am a kind, generous, and caring person. Okay, so we want to make this 4i go away down here, right? That's the one that we need to make go away. So we can do I times row 1 plus row 2 get sent to row 2. Making sense? I times row 1 plus row 2 gets sent to row 2. that is going to give me negative 4 and 4i. That one's obviously going to be a 0. And then the next one is going to be 4i squared plus 4, right? That's that entry in the bottom right, 4i squared plus 4. But I squared is equal to negative 1, so that entry just goes to 0. If you don't want to write it out, if you just want to put a 0 there, you absolutely can. If you want to write it out and then simplify, that's fine too. Either way. Okay, so here's my equation. I have negative 4v1 plus 4i v2 equals 0. Remember, my column headings are v1 and v2. That's what I'm trying to find in this case. And remember, I hid the zeros on the right-hand side because they just totally stay. So negative 4v1 plus 4i v2 equals 0. We can choose. We can choose whatever we want. It doesn't make a difference. So choosing, in this case, let's go with v1 equals I, because there's i's in the second part, so I might as well choose v1 equals I. And then do some quick algebra fingers for me, please. If v1 is equal to I, what does v2 have to equal? Do a little bit of quick mental math and hold up some fingers for me. v2 has to equal 1, 1. Good. All right, so v2 equals 1. Okay, so that means that my vector x is e to the 3 plus 4i, that's my lambda, 3 plus 4i t times the vector I1. That's my vector x. 3 plus 4i t times the vector I1. Hanging with me so far? 3 plus 4i times t times the vector I1. All good? Okay, I don't like that. So we're going to split this up. Sorry, new screen, apologies. And we're going to put this into real and complex parts. So one more time, 3 plus 4i times t times the vector I1. Okay, so we're going to use the sine and cosine parts. So here's what I have. I can do, so we can do e to the 3t times cosine of 4t plus I sine of 4t, right? We can rewrite that. E to the 4t, or e to the 3t, cosine 4t plus I sine of 4t. And then I've still got this times I1. Okay, I'm going to do 2 steps, and then in the next problem I won't write these out separately, but I'm going to do 2 separate steps here. So this is going to be I e to the 3t cosine 4t plus I squared e to the 3t sine 4t, right? Distributing the e to the 3t times both pieces and multiplying everything times I e to the 3t cosine 4t plus I squared e to the 3t sine 4t. And then the second one just gets multiplied by 1. So it's e to the 3t cosine 4t plus I e to the 3t sine 4t. So the second one just gets multiplied by 1. One more thing, and then we can take real and imaginary parts. The I squared is negative 1, right? Remember that I squared is equal to negative 1. So I can replace that I squared with negative 1. So here's my vectors. Here's what I want. My vector x1 is the real part, and my vector x2 is the imaginary part. So let's go through and designate each of these parts, whether they're real or imaginary. We've got an I e to the 3t cosine of 4t. That's imaginary, right? It has an I in front, so it's going to go in x2. E to the 3t cosine of 4t. And like we did back in chapter 2, we're just going to leave the I off. That's okay. We talked about why we're allowed to do it in chapter 2. We're allowed to do it for the same reason here. You can choose your coefficients to make this work. Next part, negative e to the 3t sine of 4t. That's real, doesn't have any i's in it, so it goes with x1. Negative e to the 3t sine of 4t. That's the real part, it goes with x1. Second row, that first part goes with x1, e to the 3t cosine 4t. That doesn't have any i's, that goes with x1. And then the other part, e to the 3t sine of 4t is imaginary, and it goes with x2. So there's my two solutions. Those are particular solutions. They don't have any unspecified constants in them, and therefore I can write my final general solution vector x as c1 vector x1 plus c2 vector x2. Final answer x as c1 vector x1 plus c2 vector x2. Or again, if you wanted to, you can make this into two functions. So little x1 of t is negative c1 e to the 3t sine 4t plus c2 e to the 3t cosine 4t. That's from the top row in my vector x, right? Top row. So I have my function x1 of t, and then I can also have my function x2 of t, c1 e to the 3t cosine 4t plus c2 e to the 3t sine 4t. So there's the two functions that are solutions if you want to write them out that way. And those are the same as the x1 and x2 that I had at the very beginning of this problem. Totally the same. Okay, I think everybody is close to caught up writing, so let me stop sharing my screen and ask if there are questions at this point. Anything for questions at this point? Daniel, yes, and then Grant will do you next. Daniel first.
Okay, so the i's, we got rid of the i's by, is that like in the constant where you're like multiplying it by I?
Yes, so yep, with a good choice of your constants, you can get rid of the i's. If you want to go back and look at chapter 2 stuff for how we actually got rid of them, I'm kind of glossing over it here. But we can do the same thing we did in chapter 2, divide into real and imaginary pieces. Yes.
Okay, thanks.
Cool. Grant, question.
When you first labeled V1 and V2, you labeled them like as the columns earlier.
Sorry, I can't hear you. When I first labeled V1 and V2.
When you first labeled V1 and V2 earlier, like in that example, you labeled them as columns, and then when you did the I1 matrix, you did like a 2x1 instead of a 1x2. Why did
So there, V1 and V2 are always columns. They're just the answers that you come out with for the choices of coefficients. Oh, I understand your question. I got it. Here we go. So we're gonna try this and then you can tell me if I didn't answer it. So V1 is the variable that goes with this first column. V2 is the variable that goes with the second column. So I'm taking negative 4 times V1 plus 4i times V2. I would also be taking 0 times V1 plus 0 times V2, but I don't need that. So I'm just labeling the columns for what those numbers go with. This first column goes with V1, negative 4 times V1, and the second column goes with V2. Did I answer your question or did I confuse you more?
No,
You're good?
Yeah.
Okay. All right. Other questions on this process? Other ones here before we do another example? Anything else? Okay. Really, it's the same idea. It just gets a little more complicated with the elementary row operations because you've got complex numbers that you're working with, right? And then it gets a little more complicated with splitting into two pieces at the very end. But other than that, it's totally the same process all the way through. It just has slight algebraic nuances, maybe.